Hello everyone, I'm here to give you a short report about my paper. I'm a PhD candidate with Professor Xiaobing Feng at Institute of Computing Technology, Chinese Academy of Sciences. Today I will show you our work about accelerating deep learning inference applications on GPUs with close-layer data reuse. Nowadays, convolution neural networks have become more and more popular with artificial intelligence and deep learning applications, including image classification and video recognition. The bottleneck of executing kernel varies depending on the applications and the GPU devices. Large-scale data transmission are bounded with memory bottleneck and complex computing tasks are usually bounded with arithmetic bandwidth. The memory access bandwidth is the potential bottleneck for accelerating neural networks, so we want to do performance optimization for convolution neural network influence on GPUs with on-chip memory data reuse. Our key idea is how to reuse data on chip. The inference systems are usually parallel and have hierarchical memory, and we get input image of chip with logic before computation and store to global memory after computation. When reusing data on chip, we need to keep the necessary data between two layers on chip and use shared memory to store instructions instead. Here is the overview workflow of our fusion strategy step by step. We get the compute graph as input. In the first step, we will do fusion analysis to find three basic modes in the compute graph for fusion. In second step, tiling the convolution operators and parallel them on GPUs. Third step, we will do memory optimization to optimize the memory access pattern for higher performance. We conclude fusion modes into three different basic types, which is somehow similar to program or code optimization types. Mode A is straight layer 1, straight 1, followed by layer 2, which can reuse the data directly. Mode B called split layer 2, and the layer 3 reuse the result of layer 1. The mode C is merge layer 3, reuse the result of both layer 1 and layer 2. There are two reasons that we choose such three simple fusion modes for fusing the layers. The one is GPU resources are limited, such as limited amount of registers and limited size of shared memory. Too much fused layers may achieve worse performance. Another reason is CNNs are complex and have different architectures. Applying these simple modes can achieve more optimization opportunities. These three basic modes can be widely found in most deep neural networks. In Figure 5a, the inception model for fusion strategy is shown, which includes two modes A and one mode B. As shown in Figure 5b, the residual connection, which is widely used in famous neural networks called ResNet, is divided into two fusion blocks, one mode A and one mode C. GPU memory hierarchy are complex and have multi-levels. You should know the different memory usage before reusing the on-chip data. Registers are fast and close to arithmetic hardware. Each thread can only access its own registers, but there are limited quantity, which depends on the number of threads launched each string multiprocessor. Shared memory is on-chip memory and shared among each block. It It also has limited size, depends on the warps on each SM. Shared memory also have some problem, leads to the throughput decreasing, called bank conflict, which happen when accessing the same word at the same clock. Textual memory and global memory are off-chip memory. Textual memory is read-only, which is faster than global memory. The average latency of global memory is about 7,000 times higher than the register latency and 5 times higher than the shared memory latency. When we hope to reuse the data between two layers, we should keep the necessary data on the same chip or on the same SM. So how to parallel on GPUs? Tiling is an important parallel strategy on GPU programming. Fusing multi-CN layers into a single kernel is a challenge because of the size of convolution filters are different and will influence the performance and the tiling strategy. Our tiling strategy is to tie each output image or feature maps into small tiles on the dimension of height and the width, not channel. The impli- and we implement implicit GMM convolution algorithm. Re redundant data storage will also be kept on shared memory each block. As shown in Figure 6, the tiling size of 3 multiplied 3 will make 36 elements stored on the GPUs, while the input size is 25. We also need to trade off while choosing tiling size. If we choose small size of tile, we will get too much redundant storage and computation. However, large size is not always good because of limited size of shared memory and registers. If we use too much shared memory or registers, we will get bad performance. To this end, we design a simple tuning rule to find a relatively optimal tiling size. More details, please refer to our paper. Um, Here is some more memory usage details. We insert synchronization primitives to ensure the correctness of the data before the second layer used in the shared memory. We use read-only cache when reading constant data with restrict type qualifiers because it is easier to use than textual memory and faster than LDG primitive. We also noticed that we should avoid shared memory conflict and we need to have enough warps for latency hiding. Now let me show you the some experiment details. We implement our layer fusion method with four representative neural network architecture: GoogleNet, MobileNet, SqueezeNet, and ResNet. The performance of different applications is often strongly influenced by parallel strategies and the memory access pattern. We conducted the experiments on two different GPU devices, NVIDIA Titan XP and Tesla P4. The first machine achieves a peak throughput of 12.15 teraflops and the P4 gets 5.5 teraflops. Finally, we get 2.02 times CUDA library on average performance and 1.5 times at least and more than 10 times at most. To clarify the effectiveness of the whole neural network with our method, we conduct the fusion method on the SqueezeNet. We use fusion strategy only on each blocks and generate the single layer with our tiling strategy. And we got 1.57 times CUDA library on the end-to-end experiments. some simple analysis also conducted. The profiling analysis is conducted on the kernels to find out the relationship between our method and coding on memory and computation. We get these profiling metrics on GPU memory from NVProof tools. We use executed load and store instructions to get the overall memory instructions. We use global memory store transactions to get the global memory operations. We get more load and store instructions and less global memory transactions because our work reduces the memory global memory operations. Obviously, our work have redundant calculation, which is more than baseline library. So with the redundant calculation and the memory operation, we still get speed up. To conclude our work, first we summarize three basic and simple fusion modes: straight, merge, and split. Then we propose a fusion method and parallel strategy that can reuse on-chip memory. Finally, the experiments show that the data reuse with on-chip memory makes sense because we get 2.02 times and 1.57 times speed up on GPUs, which is faster than existing libraries. Thank you for listening. If you have any more questions, please contact me.